So here we start. So now let us introduce ourselves. So this project is about the MFI competition on the Quaggle. It is the MFI accuracy. So my name is Zhang Ruilin, and
My name is Shi Xiao.
yeah. So now let me introduce some introduction part and some method first. So for the first part, we make a small introduction about the MFI project. It is about forecasting the daily sales of thousands products in the historical sale date, calendar events, and other informations. So we use the neutral network. We use the long short-term memory, the LSTM neutral network, and we test the performance while different layers and while adding the transformer layers. So let's first introduce the LSTM models. So LSTM model is a well-established type of recurrent neutral network. So it is a generalization of the RNN network, and it is designed to address the limitation of the traditional RNNs in handling long-term dependency. And at the heart of LSTM is a unique cell state, which updates each step via three gates: the forge gate, the input gate, and the output gate. So the second tools we will use is transformer layers. A transformer layer model sequence data by combining a self-attention mechanism and the feed-forward network. So with the attention mechanism, it will usually the residual connection will be more stabilized. So following, we will introduce our LSTM based approach. So my partner will go on the steps.
Okay, in the context of the MO competition, our initial STM model consists of a single layer encoder decoder architecture, and what we do is we deeper the LSTM architectures. So in the first part, we compare the initial LSTM architecture and the deeper LSTM architecture. The result is shown in table 1. First, we research one layer LSTM, and we also research 4 layer STM and 6 layer STM. And from the table, we can see that although the 4 layer STM model outperformed the single layer version, but it doesn't mean that the more layer you have, the better results you achieve, because the 6 layer model did not yield significant improvements. So this observation suggests that while deeper architecture can enhance representational power, they also introduce complexities that may lead to diminished returns or even overfitting. And the second part of section 2 is that we compare the LSTM with 4 layers and LSTM with 4 layers plus 1 transform layer, and the result is shown in table 2. So the second row is the result of our 4 layer LSTM, and the third row is about the 4 layers LSTM and plus 1 transformer. And although we want that the third row will achieve better results than the second row, but it is not, because although the transformer can combine more useful results, but it will face one problem, that is the hyperparameter tuning, because we have more complex gradients. So we did not achieve good results, and this is what we want to do later.
Yeah. So in conclusion, in this project, we explored the application of deep learning architecture to MFI forecasting accuracy competition, and we focus on the LSTM based models. We introduced the deeper layer and the transform layer. So these findings underscore the importance of architecture, and in the future step, we will focus on more refined hybrid designs, better normalization strategies, and we will also use the pre-train attention layers to stabilize the training and unlock the full potential of the attention mechanism in time series forecasting. So our source code was put in the website in the screen, and we also want to express our sincere gratitude to Professor Yao Yuan, our statistic machine learning course instructor, for his invaluable guidance and support. And his lecture and insight greatly enhance our understanding of machine learning principles, particularly in the neural network. And we also like to acknowledge Quagga user Koshimi, and whose code serve a foundation of our interpretation. And his work was very useful. We gain a lot of insight in the in the performance of tuning neural networks. So that would be all of our work.